let me introduce our first speaker. So our first speaker is Savvy Liu, who's a PhD student from Stanford University, and she'll be presenting her work on improving the energy efficiency and robustness of tinyML computer vision using log gradient input images. Savvy, take it away.
Hi, I'm happy to be here sharing our work in the past year and see if we can get some interesting ideas or collaborations out of it. Basically what we did was feeding log gradients to convolutional neural networks, and we achieved significant model compression as well as illumination robustness. So in a conventional computer vision pipeline, at first the image sensor captures raw pixels and then send these pixels to image signal processor for multi-stage processing, including demosaiccing, white balance, and like tone mapping, etc., etc. And then at last, the highly compressed JPEGs are fed into convolutional neural networks for specific tasks like classification, object detection, and segmentation. So this pipeline was originally designed for human perception. In the context of tinyML, there are two mismatches. First, in terms of the power requirements, because this pipeline is in general very energy hungry. And second, in terms of the data consumer, because now it's machine instead of human eyes. To squeeze this pipeline into tiny computer vision, the improvements are usually done in several modules, are done in each module separately. For example, we might use lower resolution sensors or skip stages in image signal processor, or the widely investigated CN compression, such as pruning and quantization and architecture search. Let me reiterate that all of the improvements are usually done separately. So instead, our solution is to do a hardware algorithm co-design by using an imager that outputs log gradients instead of raw pixels, and send these pixels directly to the CNN for classification or other downstream tasks. In experiment, we used raw images and then compute log gradients in the digital domain and further send these log gradients to convolutional neural networks for classification. So how do we compute log gradients from raw images? Take one image of dimension h times w. We first compute the log of pixels. Like here the +1 is to shift the unsigned integers into the domain of log. And then we extract both the horizontal edges and the vertical edges by using this gradient filter F. At last, we quantize the floating point log gradients with empirical thresholds. I give an example here. If we use a 16-bit raw image, the log gradients will range in about -22 to +22, and then we can just select two symmetric thresholds for 1.5-bit quantization. Here, 1.5-bit quantization corresponds to, as I said, two thresholds. So this looks like a lot of computation, right? But actually, no. If we look at the math, the gradient or the difference between log pixels are just the log of the ratios between two pixels. In that case, if we quantize them, we can simply use a ratio to digital converter and drop the log. One benefit of using log gradients is illumination invariance. So for illumination change, we can approximate it as a linear scaling plus clipping. For the linear scaling part, in the log of pixel ratios, if we scale each pixel by the same factor A, it got canceled out. That's why we have a illumination invariance. And on the other hand, if we consider how convolutional neural networks classify each image, what it used was basically just pattern matching. It matches the pattern between the filters or the kernels with the objects in the image. In this case, we might expect we expect a reduction in the number of filters needed. For example, here I showed a car under 4 illumination levels. If we want to detect all three windows here, we might need 3 filters for the raw image. Instead, in comparison for the log gradients, all of the illuminations are normalized to the same level. So this means we only need 1 filter to detect all of the windows. Then this is what I meant by the fewer filters here. I want to point out that this is only an intuition for our motivation next. If we put all of the energy breakdown of all 3 pipelines, we can see a significant reduction from convolutional, from conventional computer vision to tiny computer vision, and then to our log gradient computer vision. So the power savings do not come only from the log gradient imager. It also comes from the compression of scenes as I explained. I mean the intuition we just talked about. So that was just an assumption. Next, I'm going to show that convolutional networks here are actually smaller. We proved this from two perspectives. The first one is architecture search, to directly observe if we get smaller models. And the next one, and another one is kind of not that straightforward. It's a fixed architecture convolutional neural network, and to check the prunability. To show the advantages of our method, we provide 2 baselines. That's a JPEG. 8-bit JPEG, what's normally used in the computer vision, like in the ImageNet or COCO or VWW. All the images in the datasets are 8-bit JPEGs. And another one is a RAW to prove something I'm going to talk about. And at last, the log gradients. The log gradients, we checked 3 precisions. First one is the expensive floating point, and next is a 1.5-bit precision. That's 2 quantization levels. And the last one, 2.25, that's 4 quantization levels. Okay. The data set we use is a Pascal RAW 2014. That's namely, it's a raw data set. All of the images are before the ISP. No ISP was applied, with only like the demosaiking to remove the nonlinearity in between. And all the images are grayscale. Another point is the images are all from the same sensor, as well as the data size of only 6K. I feel all of these settings are are closer to what we are going to apply in the real world. And I also want to talk a little bit about the visual wake words dataset. Since even though the visual wake words dataset have a lot of images, like 123K, that's much more than the 6K we have here. But why don't we use the visual wake words? First of all, it's because of the data, the image format. As I mentioned, all of the images here are JPEG images. It's highly compressed. From raw images, and the mapping is not one-to-one, so we cannot recover the lost information from JPEG images. Now let's dive into the experiments. The first experiments we did is an architecture search. We use an algorithm that's specially designed for microcontrollers. It sets bounds on 3 key resources. The first one, the 3 key resources like max, model size, and as well as peak memory usage. And on this slide, we compare 3 key image types we fed into the MUNARs. The first one is a 8-bit JPEG representing representing the conventional way in tinyVision, the conventional pipeline. And the second, the second one is a 16-bit raw to show if we can use ISP or what role ISP plays in machine learning. And last is our pipeline. Here I show the floating point log gradients. By observing the Pareto fronts of all 3 key resources, we can see the log gradients push the fronts significantly from here to here. And we can see on the x-axis is error rate. If we look at the lowest error rate, we can conclude that our pipeline of using log gradients have the highest achievable accuracy. And for a given accuracy or error rate, the resources consumption can be orders of magnitude lower than the conventional method, either JPEG or 16-bit RAW. Another point I want to talk about is between the RAW and JPEG, because we can see the JPEGs actually have some advantages, which is consistent with some other works in our community, in the tinyML community. Now let's look at the quantization. Even though we see a significant, we decrease the precision drastically from floating point to 2.25 bit and then to 1.5 bit. The performance drop is not that high according to as expected. So you can see here, even though there are like the Pareto fronts are pushed away from optimal, it's still comparable with the baseline that's 8-bit JPEG produced by conventional pipelines. So our takeaway from previous 2 slides is that according to MUNARs, according to the architecture search, our pipeline using log gradients actually needs smaller models. So I want to go back to our intuition page here to see if the MUNARs experiments verify this intuition. But unfortunately, the MUNARs architectures are very complicated. It's complicated because it has multiple parallel blocks, making it very hard to analyze about if the savings are because if we have any kind of filters savings. Therefore, we did a more straightforward experiments by using a toy convolutional neural network that's only 2 convolution layers. And we set the number of filters in the first layer high to about 150, and then compute the cosine similarity as a measure of redundancy. So here, if the cosine similarity equals 1, it means the 2 filters, or the 2 filters are just exactly the same. That's duplicate. That means we can remove all those duplicate filters. And this is just the cumulative histogram of cosine similarity. So the takeaway for this slide is that log gradient has more duplicate filters, and therefore more redundancy and more pruning. If you still feel kind of confused about what I just said, I'm going to emphasize it here a little bit. And for the filter similarity, redundancy, and prunability, I compared 2 pipelines. For the first so what we observed is that more filters in using log gradients are similar. So for example, here for the raw or JPEG, it's only 3 duplicate filters, and here I have 16. And then this means we might be able to remove all of the duplicate filters. In this case, we can remove 2, and here we can remove 15 to reserve only 1 for 1 object. The result is that we will have a smaller neural network. But I just showed the relationship between prunability, filter similarity, and redundancy. I didn't theoretically show or just prove it by experiments. This is what I'm going to do right now. So I fixed the second layer, fix the number of filters of the second layer to 8, and vary the number of filters in the first layer. If our intuition stands, we will need a smaller C1 here. This is exactly what we observed. So for this figure, if we increase the number of C1, we can see the accuracy keeps improving. That's expected because the convolutional neural networks just get larger. It has more power to fit in the data. And if we, for a fixed accuracy, if we draw a horizontal line here, we can see for the log gradients, it only needs 2 filters, while the baseline, the conventional computer vision pipeline needs more than 4, and for the raw, it needs even more than 16. So log gradients does need fewer filters in the first convolutional layer. Here is here is also to validate our argument that we have illumination invariance. So all the neural networks trained are at the baseline. The brightness factor of the training set is 1, and then we vary the brightness factor of the test set. So we can see either in 2 directions. If the images get darker, log gradients didn't lose any performance. So it's like here the horizontal line for the accuracy. And however, for the other 2, both the JPEG and the RAW, it drops significantly. And in the opposite direction, if the images get brighter, our log gradients also drops. Our log gradients also drop, but at a slower rate. So in summary, we use a log gradient. We use a log gradient pipeline, and then prove it with 2 experiments that the convolutional neural networks will allow more compression. The two experiments are architecture search and fixed CN architectures. In the future, we would like to explore quantizer training because right now the internal precision is floating point. It's very expensive. And another thing is threshold search for the quantization of log gradients, and that is adversarial robustness. Thank you all. Do you have any questions?
So I have one question. So I see it's very interesting, but my question is that actually I have two questions. One is that because this is applied for the first layer only, I guess. So I want to know.
I'm sorry, can you be a little bit louder?
So because the log gradient is applied on the image and potentially the very early layer initially, so do you have a comparison towards like at the overall like energy perspective or like complexity perspective? How much does this early layers compare to like the later stages?
I'm sorry, I couldn't hear you.
Yeah, so because this technique is mostly applied for the early phase of the recognition or the machine learning task. So I want to know.
Oh, you mean downstream tasks like the detection, segmentation? Yeah, not yet. Because
Okay.
it's like we want to see if it works in a very simple case like the classification. If it doesn't work, why would we try it?
Okay, yeah, and also another question. So because when you talk about the variance towards like the illumination, it's also indicating that, let's say, the log, this kind of gradient may be more, may kind of keep the more of this low frequency responses from the word, but may actually prune out some of the high frequency details, right? So I'm wondering, did you had experience or have you tried any other applications that focus a little bit more on the high frequency details? Like, so for example, like image reconstruction or like?
Yeah, so the basic idea is that the log, even though we have a very aggressive quantization, the quantized log gradients still preserve a lot of useful information. Here I did an image reconstruction. So from the 1.5 log gradients, I use a very simple, toy convolutional neural network to do the reconstruction, and I achieved these results. So there are just so many useful information preserved. And in terms of the frequency perspective, I actually have my own understanding because I feel the log gradients, what it did was to separate the lower frequency from the higher frequency. It's like if you think it intuitively, how we human classify an image. If you see an outline of something, and you can say, oh, it's a person, right? So we don't need to know that much information. Okay, so if do we need to know the color of his clothes to say he or she is a person? No, we don't need that.
Yeah, thank you.
All right. Thanks, Savi.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Sentient. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Gravity, Hymix, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support and, more importantly, for them being part of this community and driving it forward.